Welcome to today's paper reading. Today's paper is titled, Augmenting Large Language Models with Chemistry Tools. This paper, authored by Andres M. Bran and colleagues from the Laboratory of Artificial Chemical Intelligence, LIC, at EPFL and the Department of Chemical Engineering at the University of Rochester, discusses the integration of computational chemistry tools with large language models to enhance their performance in chemistry-related tasks. The abstract highlights the development of computational chemistry tools and their potential when integrated into a single, accessible platform. It mentions the capabilities of large language models, LLMs, in various domains but points out their limitations in chemistry and lack of access to external knowledge. The introduction of ChemCrow, an LLM chemistry agent, is discussed, which integrates 18 expert-designed tools to enhance performance in chemistry. ChemCrow's ability to automate a diverse set of chemical tasks is emphasized, along with its potential to aid both expert chemists and non-experts, and to bridge the gap between experimental and computational chemistry. Language models, particularly in the context of chemistry, have shown significant impact on various chemical tasks. However, the automation levels achieved in chemistry remain relatively low compared to other domains, primarily due to the field's highly experimental nature and the lack of data. ChemCrow, an LLM-powered chemistry engine, aims to address these challenges by integrating multiple expert-designed tools to streamline the reasoning process for various chemical tasks. Despite the potential, the integration of such tools often occurs within isolated environments, posing challenges for experimental chemists due to their lack of computational skills and the diversity of tools with steep learning curves. Figure 1 provides an overview of the task-solving process in ChemCrow, a large language model, LLM, chemistry agent. The process involves creating a set of tools using various chemistry-related packages and software. These tools, along with user input, are given to the LLM, which then proceeds through an automatic, iterative chain of thought process. This process involves deciding on its path, choice of tools, and inputs before coming to a final answer. The example shown is the synthesis of DEET, a common insect repellent. The figure also details the tool sets implemented in ChemCrow, including reaction, molecule, safety, search, and standard tools. In the realm of autonomous chemical synthesis, ChemCrow has demonstrated its capability by successfully synthesizing DEET and thiourea organocatalysts on the RoboRxN platform. This process involves iterative adaptation to ensure the synthesis procedures are valid. Additionally, the human-AI collaboration has led to the discovery of a novel chromophore through the training and application of a machine learning model. The evaluation of these processes involves collaboration with expert chemists and comparison with GPT-4, highlighting the strengths and weaknesses of each approach. Figure 2 provides a detailed look into the experimental validation process of ChemCrow. Panel A illustrates an example script that a user might run to initiate ChemCrow, showcasing the interaction between the user and the system. Panel B delves into the query and synthesis process of a thiourea organocatalyst, highlighting the system's capabilities in chemical synthesis. Panel C presents the IBM Research RoboRxN synthesis platform, the environment in which these experiments were conducted, emphasizing the integration of advanced technology in chemical research. Finally, Panel D shows the experimentally validated compounds, demonstrating the tangible outcomes of the system's operations. Figure 3 illustrates the collaborative process between a human chemist and ChemCrow in discovering a novel chromophore. On the left, the human provides input tasks such as cleaning and pre-processing chromophore data, training a random forest model, and suggesting a synthetic plan for a molecule with an absorption maximum wavelength close to 369 nanometers. On the right, ChemCrow performs a series of actions including checking data format, filtering relevant data, calculating fingerprints, splitting datasets, training and evaluating the model, proposing molecules from a selection pool, and predicting a two-step synthetic procedure for the selected molecule. The final answer includes a synthetic plan for a molecule with a predicted absorption maximum wavelength closest to 369 nanometers, demonstrating the successful integration of human input and AI-driven actions in the discovery process. Figure 4 presents the evaluation results comparing the performance of GPT-4 and ChemCrow across various tasks. The figure is divided into 3 sections. A. Per task preference, where evaluators indicate their satisfaction with each response, categorized by task difficulty in synthesis, molecular design, and chemical logic. B. Chemical accuracy, focusing on the factual correctness of responses in organic synthesis tasks, sorted by the synthetic accessibility of targets. C. Aggregate results, showing the combined scores from human evaluators for each metric, compared to evaluator GPT scores, with error bars indicating the 95% confidence interval. This figure highlights the strengths and weaknesses of both models, particularly in tasks requiring complex chemical reasoning. The paper discusses several risk mitigation strategies for LLM-powered chemistry engines like ChemCrow. Firstly, safety guidelines are implemented to ensure that the engine follows strict safety protocols, such as stopping execution for controlled chemicals and incorporating safety information into its responses. Secondly, to address the risk of inaccurate reasoning due to limited chemistry knowledge, the paper suggests enhancing the quality and breadth of training data and implementing validation systems similar to those used in RLHF for GPT 3.5. Lastly, the paper emphasizes the importance of addressing intellectual property issues by establishing clear guidelines and collaborating with legal experts to protect generated syntheses and avoid infringement of proprietary information. Figure 5 illustrates the safety guidelines implemented by ChemCrow, focusing on the synthesis procedure for paracetamol. On the left, the molecule is checked for being a controlled chemical. Since paracetamol is not a controlled substance, the execution proceeds, incorporating general laboratory safety information. On the right, the scenario changes where the input molecule is identified as a controlled chemical. Here, ChemCrow halts the execution and issues a warning, emphasizing the illegality and unethical nature of proposing compounds with similar properties to controlled chemicals. This dual approach ensures that safety is prioritized while allowing for the synthesis of non-controlled substances. The development of ChemCrow represents a novel approach in integrating computational tools within chemistry using large language models, LLMs. This method combines the reasoning capabilities of LLMs with specialized chemical knowledge, marking one of the first instances of a chemistry-related LLM interacting with the physical world. ChemCrow has successfully demonstrated its utility by planning and synthesizing an insect repellent, 3 organocatalysts, and guiding the synthesis of a novel chromophore with targeted properties. Additionally, it can independently solve a variety of chemistry-related reasoning tasks, from simple drug discovery loops to complex synthesis planning, suggesting its potential as a future chemical assistant akin to ChatGPT. While the current evaluation shows ChemCrow outperforming GPT-4 in chemical factuality and reasoning, especially for complex tasks, there are challenges in the evaluation process that need to be addressed, such as the reproducibility of results and the selection of tasks. Despite these challenges, the results indicate a promising future for systems like ChemCrow in assisting chemical laboratories and addressing tasks across diverse chemical domains. The rise of large language models, LLMs, in recent years has significantly advanced their availability and scalability, opening up a wide range of applications. These models are particularly powerful when used within frameworks designed to exploit their zero-shot reasoning capabilities, such as React and MRKL. LangChain is a comprehensive framework that facilitates the development of language model applications by providing support for various modules, including access to different LLMs, prompts, document loaders, chains, indexes, agents, memory, and chat functionality. This framework enables users to create applications like chatbots and question-answering systems. Additionally, LangChain assists in integrating with external tools, experimenting with different prompts and models, and evaluating the performance of generative models. The tools used in our implementation can be classified into general tools, molecular tools, and chemical reaction tools, with safety assessment functionalities built in to mitigate risks. These tools also allow direct interaction with robotic chemistry lab platforms. Thank you for watching.